We are back into our lecture series on advanced hydraulics. We are in the third module on varied flows. If you recall the last class, in the last class we had discussed on the various properties of the gradually varied flow profiles. So, if you have recalled them, you have seen that the slope of the water surface, that is dy by dx, it tends to 0 when the depth of the water tends to the normal depth, or the energy slope tends to the bed slope. If these two situations are present, then you have seen that the dy by dx means the water surface is almost horizontal. If the depth of the water tends to the critical depth, then dy by dx is almost infinite. That is, the slope at the critical depth, you will see the water surface is almost perpendicular. So, it is a theoretical concept. You have also seen that at large depths, that is when y tends to infinite and all, the water surface slope, it is almost equal to the bed slope. You have also seen certain singular conditions arise. Singular conditions means when dy by dx is equal to 0 by 0 form. If these things arises, that is called singular conditions. So, singular condition arises when the normal depth is same as the critical depth and this is same as the depth of flow. We have gone through the situation where when yn, that is the normal depth, is equal to critical depth. In such situations, there exists transitional depths or transitional profiles. For that, first we have evaluated limit slope. As a demonstrative example, we had evaluated limit slope for a rectangular channel, and we also had given a theoretical procedure how to establish the transitional depth thereafter. Say this was the equation derived, if you recall them, n squared g d is equal to S 0 r to the power of 4 by 3. So, you see the transitional depths and all, they have some characteristic profiles. It is not dependent on the certain means, seen that this theoretical procedure, it depends it depends only on the channel geometry and the roughness of the channel. So, that property and all, if you see, means transitional depth is also theoretically one can establish them. In the last class, when we suggested about the discussing on the transitional depth and all, we have suggested or we have evaluated critical slope curve versus the discharge for the rectangular channel problem, whichever we had discussed in the last class. So, there you had obtained such a type of curve, and we have suggested that the minimum critical slope that can be possible in this case, that is given as the limit slope S L. If you are able to recall them. So, this is the limit slope, this value. So, it was for that particular problem, S L was almost around 0.00408, something like that. Now, your actual bed slope in the problem, it can be either less than the limit slope or it can be greater than the limit slope. What are the different conditions for transitional depths? Means, suppose if you want to compute or if you want to observe the transitional depths or transitional profile, how will you proceed for that? So, today we will see some of the gradually varied flow profile computational methods. So, before starting the computational methods, we will quickly glance through how the transitional profiles, especially in the transitional cases and all, how one can evaluate the transitional depths or how you can observe it in the channel cross section and all. So, recall the same graph. So, as we mentioned earlier, this is your limit slope S L. Now, if the actual bed slope of the channel for the given discharge, if the actual bed slope of the channel, if it is less than the limit slope, that is somewhere here, if your bed slope is somewhere here, then what happens? this is the critical slope line. So, your slope S0 is less than SL, means subcritical flow exists, right. So, it is a subcritical flow, and in subcritical flow, what is the gradually varied flow profile that you can observe in such situation? Yes. So, it is the same M1 profile that you can observe. You see here, this is the channel cross section. Suppose if you are creating a bunt, then this is your critical depth, it is your initial normal depth, then the gradually varied profile will be something of this form. Fine. This will be the gradually varied flow profile. So, here in such situation there will not be any transitional depths and dot, because your bed slope is already less than the critical limit slope. So, it is a subcritical flow existing there. What happens to the next situation? If your bed slope is greater than the limit slope, then let us see that how you can demonstrate. This is your limit slope. So, if your bed slope is greater than, say let this be your bed slope S0. If this is greater than the limit slope, then you can observe easily two discharges. Say this is discharge, I can write it as QA, and this is discharge QB. That is, for the same bed slope S0, for S0 can become critical slope for discharges QA and QB. So, from this profile you can see that. So, S0 at this location for almost magnitude of 2, it is the QA, that is QA is equal to 2 meter cube per second in this from this particular graph. So, it is almost the bed slope is almost a critical slope. Similarly, just above 4 between 4 and 5 here QB, the magnitude of QB, at that situation also S0 is acting as a critical slope. Like that you can easily observe them. So, how can you observe the transitional profiles in such situations? So, it depends on what is your actual discharge Q. Say if your actual discharge Q, if it is less than QA, even though your bed slope is S0, if Q is less than QA, from this graph, when do you think that Q can become less than QA? It can become less than QA only if the corresponding slope is greater than S0, right. Say somewhere here, this is Q, some actual Q value. So, this is some S, some particular slope S. So, for that Q, the critical slope SC is at this location, but the actual bed slope is S0. So, S0 in such situation is less than the critical slope. Therefore, again the subcritical flow with M1 profile will exist, fine, because the gradually varied flow profile contains 2 points. You know that for QA there is one particular depth YA, for QB there is another particular depth YB. If I want to plot them, say your bed profile initially the normal depth y n, you have the critical depth y c. So, in this normal depth, this is going to follow an M1 profile. So, you know that this will gradually increase like this, and then right. So, this is a gradually varied flow profile. In that case, there exist 2 points, say T A on the profile, there exist 2 points T A and T B. Okay. There exist 2 points. Why we are mentioning such 2 points are, so the corresponding depths will be y A and y B. So, these points y A and y B represents the normal discharge Q A and Q B. So, T A at these locations, the gradually varied flow profile will be horizontal. So, they are the points of inflection, that is the slope changes from that location onwards, the slope of the curve changes from that location onwards. So, such horizontal. So, these T A points T A and T B are the transitional locations, transitional depths are then the corresponding y A and y B. Fine. Similarly, you can explain for a situation if Q is slightly greater than Q A, but however less than Q B. Then in that situation, your bed slope will be greater than the critical slope and your supercritical flow will be having S profiles. So, that S profile one can think of in the following form. So, initially if this is your normal depth, if this is the critical depth line, then your profile initially it will be in the following form up to a certain location T A. There the slope will be horizontal, water surface profile will be horizontal, then it will make a jump and will have S1 profile. So, it will go through it will be having S3 and S1 curves, right. It will be having S3 and S1 curves. So, using these theoretical knowledge and all, now we will to see what are the various methods of computing gradually varied flow profiles. Right. So, let me recall the dynamic equation for gradually varied flow. Dy by dx, this is equal to S0 1 minus k n by k whole squared by 1 minus, I beg pardon, z c by z whole square. This you can write in terms of y also, we have derived it in the last class, 1 minus y n by y whole to the power of hydraulic exponent n divided by 1 minus y c by y whole to the power of m. So, you can see that this is a first order differential equation in y, and we have it is a first order differential equation in y. So, we have seen also seen that it requires one boundary condition to solve, And also to solve that, we have described the control sections in the open channel flows. One can begin with the control sections where the properties are known initially, and from there one can start computing the profile, like that we have discussed in the last class about the control sections. So, based on one control section, one can easily start the profile computations. Solving this differential equation means you can identify the distance for a particular depth of flow, how much it is, how much distance it is from the control section, whichever referred control section is there, how much distance it is from that control section, that you can identify. Or for a given distance from the control section, what could be the depth of the water profile, that can also be identified from solving these equations. In general, to solve a differential equation, the various methods you have are analytical methods. You can also use semi-analytical methods. You can also use graphical methods, and the most common and more widely used method is the numerical methods. So, you can use any of these methods to solve the differential equation, that is the dynamic equation for gradually varied flow. So, to solve these equations, analytical methods, it is possible only for very few cases, very few simple cases only. One can solve the gradually varied flow problem using analytical methods. Semi-analytical methods, it involves where, as you have seen this differential equation, to solve this differential equation means you have to integrate upon y and x, right, the equation. That is the meaning of solving the differential equation. So, that means in semi-analytical form, what you are doing is that you are clubbing the actual integration with certain numerical integration approximations that are available for some functions. For example, if you have cosine function, there can be a tabular values of cosine function, numerically integrated values for the cosine function, and you can directly substitute them, and like that you can develop the semi-analytical solution. If you have sine function or if you have exponential function, based on that one can, in a tabular form, if it is already available, the tabular data or tabular things are already available, the integrated values for those functions, and you can directly substitute. That is the approach used in semi-analytical form. Graphical form, what you are doing is that you are just directly plotting the slope of the curve versus the depth of the curve directly, and from that you just compute the area, say dx by dy, inverse of the slope. One can just plot like that and then try to club it. That is also possible. Dy by dx with y, that can also be plotted, and you can compute the area graphically. Graphically, the area has to be computed. So, this is a very tedious, although the approach is correct and it may give a very good result, it is quite tedious. So, the graphical method is quite tedious. The most common method is the numerical method. Due to the advancement in the computational technology and all, one can readily use the numerical methods to solve such type of differential equation. Not only such differential equation, even the higher order differential equations are also solved using numerical methods. Very common very common methods like finite difference method, finite element methods and all, you might have already seen them in some of your other courses. They can be used here in the open channel flow also. So, some of the in the analytical and semi-analytical method, I will just briefly describe one or two methods here. we are definitely these methods are not going to help you solve the practical problems. They can be only used in a very limited situation, where especially in the laboratory cases where you have all the constraints established. In such situations only one will be able to solve the gradually varied flow equation, dynamic equation using analytical form. So, here the analytical methods, they were developed quite earlier itself in the earlier part of the 20th century or in the later part of the 19th century, and all their mathematicians have developed analytical forms for these equations. We will just briefly go through them. I am not going to discuss elaborately on those things. So, your governing dynamic equation, if I write it in the terms of depth of flow, y c by y whole to the power of m. So, where n and m are hydraulic exponents that you are quite aware right now. Y n is the normal depth, y c is the critical depth. If you recall in the module 2, in module 2 we had discussed on the hydraulic exponents n and m for various type of channels, for rectangular channels, for wide rectangular channels, and for trapezoidal channels. We had in fact derived the expressions for n and m also. You just refer back them. For a simple case, for a wide rectangular channel, using those relationships for a wide rectangular channel, it is observed that your hydraulic exponent n is equal to 3. Now, for a situation where n is equal to m is equal to 3, if you take this thing and if you had used Chassis equation for computing section factors, instead of Manning's equation, if you have used Chassis equation for computing section factors in critical flow and all, then you will observe that this particular dynamic equation can be solved with the following expression. The solution can be given in the following form: x, that is the distance, horizontal distance x, this is equal to y n by S 0 into u minus 1 minus y c by y n whole cube into 1 by 6th of natural log of u squared plus u plus 1 by u minus 1 whole squared minus 1 by root 3 arctan of root 3 by 2 u plus 1, this square bracket is closed, plus some constant of integration C I. Like this, one can give a solution for the dynamic equation where x is the horizontal distance, u is the normalized depth, that is given as y by y n. C I is equal to constant of integration your C I, then all other terms are explained earlier also. So, using this relationship you can obtain the solution for the gradually, or this is the solution for the gradually varied flow profile From this you can easily determine the horizontal length of the profile and so or horizontal location of the for a particular depth, what is the corresponding horizontal distance, that can also be identified from this equation. So, this solution was obtained by Bresci in 1860. So, you see it was long back in the 19th century itself such a solution was identified. So, this is called the famous Bresci solution for gradually varied flow profile. Although this solution, it is obsolete in the present generation, but still you can appreciate long back, even in almost 200 years before itself, more than 200 years before itself, or nearly 200 years before, scientists had almost reached for an approximate solutions or a nearby solutions to the flow problems. So, that way the science has to be quite appreciated. A semi-analytical form which I would like to briefly introduce to you is the following form: semi-analytical solution. So, the semi-analytical solutions, they are usually obtained, means in the open channel for gradually varied flow, they are usually done by generating varied flow functions. Such varied flow functions, different type of varied flow functions, they were developed by Bakhmetev. In 1910s, around between 1910 1920 and all, varied flow functions were derived, mathematical varied flow functions were derived by Bakhmetev. Such functions were later used by Wenty Chow in 1955 in his book on open channel hydraulics and all. He has used the varied flow functions and obtained flow profiles or obtained solutions for the gradually varied flow profile equation. So, one such solution is your horizontal distance x is equal to y n by S naught into u minus the varied flow function f of u and hydraulic exponent n plus a parameter j divided by n into y c by y n raised to m into the varied flow function of a variable v and parameter j plus constant of integration C n, where u is your normalized depth y by y n, j is a parameter obtained as n by n minus m plus 1. If you have recalled in the hydraulic exponent literature and all, whichever we have dealt in the module 2, there also we had encountered with similar relationship. So, it is the same thing. So, j, you have just substituted the quantity j here. The variable v is nothing but it is u to the power of n by j. Like this you can obtain the variable v, and your varied flow function f of any two parameters a and b, it is given as integral of 0 to a dx by 1 minus x to the power of b, like this, and this is called varied flow function. So, you can use these semi-analytical forms. So, the tabular values of these functions, varied flow functions, they are available in the literature, especially if you go through the Vinci Chow's book on open channel hydraulics and all, you will get varied flow functions for different parameters. You can directly substitute them. So, this is a semi-analytical approach. One can use the semi-analytical approach also for solving the gradually varied flow problem. So, but as we have mentioned earlier, there is graphical method also. Of course, we are not going to do the graphical method, but this can also be used to solve the gradually varied flow. The fundamental is dy by dx. This is S0 minus SF by 1 minus q square t by GAQ. In the beginning of this module, we have been discussing on this dynamic equation. So, please recall them. So, this can be written as S0 minus SF is given using Manning's equation, n squared q squared by a squared r to the power of 4 by 3 divided by 1 minus q squared t by GAQ. So, what do you infer from this? You can write the inverse of this differential equation dx by dy is equal to 1 minus q squared t by g a cube by s 0 minus n squared q squared by a squared r to the power of 4 by 3. You can integrate them. So, on integrating them, on the left hand side you integrate it with dx, and this term you integrate it with respect to dy. You are going to solve x in term with respect to y. Like this, you are able to get the term. This can be done in a manual form or in a graphical form also. One can easily plot them, y versus dx by dy, and the corresponding plot whichever you are getting, you just compute the area. You just compute it manually, that from that graph what is the area, and that area will give you the distance x. Okay. Or suppose if you want to measure y, go through the reverse process. You plot x with respect to dy by dx, then you plot them and you will get the corresponding y value. So, the most important method which we hereafter will be always referring is the numerical methods. The idea behind numerical methods, it is an approximate method for solving differential equation. It is not the direct method whichever you have studied in your high school levels or even in your college levels and all. The numerical method does not follow the direct approach. It is an approximate approach. Here the idea or the crux behind solving the differential equation is you are going to approximate the various functions or derivatives in the differential equation with certain algebraic expressions. Once you are able to substitute it with algebraic expression, then that corresponding differential equation is converted to an algebraic equation. You can further solve the algebraic equation in easier manner. You are already aware how the linear algebra or the linear algebraic equation is much easier to solve compared to many tough differential equations, right. So, the numerical methods is just converting the differential form into algebraic form, and then you are solving the corresponding value. So, that is the crux behind here. So, the computers of late, you know that the memory as well as the computational speed in many of the things, it has been increased tremendously. So, there is no limit in computations now, and you can use n number of infinite, almost you can say quote it as infinite number of unknown things and try to inverse them, try to solve them. The computational capability is that high nowadays. So, due to this computational one can easily go for the computational approach and solve the open channel flow problem. Why you need to manually go and try to do it analytically, if your computer is able to solve them easily in few seconds. That is the idea behind using numerical methods, as well as the difficulty in the analytical approach. So, let me tell you. So, in the numerical methods for the open channel flow, we will consider, say, using numerical methods we can find distance between two sections. You can find distance between two sections if depths are specified. Or you can compute depths where distance to those cross sections are specified from control section, of course. So, that is, say, if I just draw it like this, say if this is your control section for a particular problem, then you know that this you can consider it x is equal to 0. From this location you can compute profile in the upstream direction, say x, this is x. So, for this at this location, what is the depth of water y, that can be obtained as per the second statement, or from this control section, if you are given a certain depth y 1, what is the corresponding distance x, that can also be identified. So, one can easily use the numerical methods. So, here what we are going to do is that approximate the derivative in the gradually varied flow equation with an algebraic expression. So, usually what we are doing is that this is the derivative available. So, dy by dx is now approximated by an expression, algebraic expression in the form of y 2 minus y 1 by x 2 minus x 1. That is, say, from the control section, if you have two locations, this is x 1, this is x 2 and the corresponding depths of y 1 and y 2. If you have them, then the slope of water surface dy by dx between these two sections can be approximated by the following algebraic expression y 2 minus y 1 by x 2 minus x 1. This has been obtained from Taylor's series. If you refer further the numerical methods book and all, it will be quite clear. So, such approximation is done. Then all other terms which involves the quantities or all other functions that are related to depth, they can be averaged also accordingly, and you can use them in the equation. So, not only the differential equation, if it is a partial differential equation, the partial derivatives are also substituted by algebraic terms, and the corresponding equation becomes an algebraic equation. So, that algebraic equation is solved. So, that is the objective here. The first method which we are going to do is direct step method. The first method is direct step method. What we are going to do is the channel reach, whichever channel reach is there. See, if there is an obstruction and gradually flow profile is there, it is the channel reach is now divided into short reaches. You will compute the properties now in each of the small reaches, then you club them, or you say from if this is your control section, then from the control section you begin the thing. From the control section you know all the properties, then you compute here in this portion, then here, using the values here you compute it here, then using the values here you compute it here, like this you will go on. So, this is a step by step approach. So, you can use the step method to compute flow or compute the flow properties. Just recall your specific energy equation, y plus q squared by 2 g a squared. So, the direct step method we can use mostly for the prismatic sections only. For non-prismatic sections, this method is not that convenient. So, we will see it later. So, please note that this is how you are going to use them. You have also seen that dE by dx is equal to S0 minus SF in one of our earlier lectures. So, what does this mean? Change in energy. So, this thing you are now going to use this derivative, you are going to approximate it using algebraic expression. Del E by del x is equal to S0 minus SF, like this you can write, or del x, change in distance or the difference or the distance between 2 points, del x, that can be given as change in specific energy between those 2 points by S0 minus SF. Now, in this case SF you have to take as the average one. Difference in specific energy between two sections. So, this is equal to E 2 minus, if you have two sections 1 and 2, say in the reach 1 1 2 2. So, E 2 minus E 1. SF we are taking the average value, it is the average frictional slope. It is the average frictional slope between the two sections 1 1 and 2 2. So, it is generally given as 0.5 into SF1 plus SF2, like this you can give them. Del E is equal to E 2 minus E 1. Using this thing, one can now compute del x. If you are able to compute del E by S0, you can then further compute the distance between 2 points del x. A demonstrative problem will help you in solving this thing. Let us show that example. So, please note this particular problem. A rectangular channel of width b is equal to 2 meter and 50 meter long allows water to free fall. The channel is made of glass, that is Manning's n is equal to 0.01. The bed drops by 5 centimeter in entire length. So, you have the length like this. So, 50 meter length, channel width is 2 meter. So, it is allowing free fall from this edge. So, this is the brink. The bed drops by 5 centimeter in the entire length, from here to here it drops 5 centimeter. At channel entrance the depth is observed to be a constant. Here the depth is almost observed to be a constant of 0.5 meters. Find the length of the gradually varied flow profile. From the free fall brink, that is from here to a particular section here, where the depth y is equal to 0.45. What is the length of the profile L? That is what we have to do it now. Use the direct step method. So, let us see the thing. You know, discharge q is equal to 1 by n a r to the power of 2 by 3 s naught to the power of half, a is equal to b y. So, in the beginning, in the entrance, channel entrance, you will see that this is nothing but 2 into 0.5 is equal to 1 meter square. Then you have b is equal to 2, wetted perimeter is equal to 2 plus 1 is equal to 3 meter, r is equal to 1 by 3, your bed slope S 0 is equal to 0.05 by 50. So, this is 1 into 10 to the power of minus 3. So, if you have these things, q substituting these values, it is observed to be 1.5203 meter cube per second. This is the observed discharge. Now, for that, let me suggest you the same discharge at the brink, say at the brink, here the depth will be critical depth. So, the critical depth you can easily compute for the rectangular channel as b squared g power of 1 by 3. Substitute the values 1.5203 by 2 squared into 9.81 whole to the power of 1 by 3. So, your critical depth is observed to be 3891 meters. Okay. So, the critical depth for the flow is 0.3891. So, at the brink the depth is 0.3891. Now, the total length of the profile between this location 0.3891 and somewhere here y is equal to 0.45. So, what is this length? That is the question asked to you, and we are now going to do it by direct step method. So, let me do in the following form. As y c is equal to 0.3891, I am taking another depth y is equal to 0.41, another depth y is equal to 0.43. Like that, I am going to take 3 sections, 1, 2, 3. The distance in each section, this is del x 1, this is del x 2, this is del x. The summation of del x 1, del x 2, del x 3, that will give you the total length of the profile. So, that I am just going to do it. So, now for each of these sections, small portions, small reaches, I will be computing the corresponding distance and just computing. So, that can be done in the following table. So, for section, this is 1, 2, 3, 4. That is, here is section 1, cross section 2, cross section 3, cross section 4, and these are the reaches 1, 2, 3. So, please do not confuse with the reaches and the section. I am just rubbing it for your convenience. So, I have the corresponding section now. So, at section 1 the depth is 0.3891, you already know that we had, it is the critical depth. The corresponding area A, you know it is by, you compute it, you will get it 0.7782. The corresponding R, this is equal to A by P, I had got it as 0.2801. The corresponding energy slope SF, it is obtained as n squared q squared by a squared to the power r to the power of 4 by 3. So, this value it is coming around to be 2.0819 into 10 to the power of minus 3. Your energy E, it is nothing but y plus q squared by 2 g a squared. Substitute this form here and I am getting 0.58357. Similarly, for section 2, the corresponding depth is 0.41, at section 3 the depth is 0.43 and at section 4 the depth is 0.45. You can see the corresponding area also. The corresponding hydraulic radius, it is coming to be 0.2908 here, 0.3007, 0.3103. SF, you compute it using this relationship for each of the sections. You will see here it is 1.7837 into 10 to the power minus 3. Here it is 1.5508 into 10 to the power minus 3. Here it is 1.3579 into 10 to the power minus 3. The corresponding energies, specific energies are 0.58, 515, 0.58, 923, 0.59, 540. You can take the average of these two and write it here, average of these two, similarly average of these two like this. So, I can write the average values now. This is 1 point average SF into 10 to the power minus 3, in terms of minus 3 you can write 1.9328, 1.6625, 1.454535, like this you will get. Delhi also you can, difference between these energies, you can write them. Here it is 0.00158, 0.00408, 0.00617. So, you have got this thing, you know del x is equal to del E by S0 minus SF bar. Substitute that, I will write it again here, del x is equal to del E by S0 minus SF bar. Substitute this relationship here, you will get the corresponding del x value here as minus 1.694, this is minus 6.114 and minus 13.579. So, total length of profile L is equal to the modulus value of del x1 plus del x2 plus del x3. Substitute them, I am getting it as 21.388 meters. So, this is the length of the profile. So, this way you can do the direct step method. you can approach other methods also. We will see it in the next classes. So, today we are going to wind up the lecture. We will just have a very quick quiz session. The first question is the dynamic equation for gradually varied flow a differential equation? Now, enumerate the methods used to solve the differential equation. It takes hardly 30 seconds at home. Now, just here you just need to tick this thing. Discuss which is the correct method. Direct step method for solving gradually varied flow is, it is an analytical method or it is a semi-analytical method, it is a graphical method or it is a numerical method. Which is the right one? It is up to you to answer them. So, the solutions for the quiz. So, for the first one, of course, dynamic equation is a differential equation. We have seen the various methods are different: analytical method, semi-analytical method, graphical method and numerical method. For the second question, you know the correct method. The correct method here it is the numerical method. So, we will continue with the similar topic in the next class. Thank you.